Let me quickly introduce the speaker for today, Dr. T.V. Prabhakar. Dr. T.V. Prabhakar is a principal research scientist at the Department of Electronic System Engineering and IISc. He works in the area of networked embedded systems, where he focuses on hardware system design, micro energy harvesting systems, and power management algorithms. Dr. Prabhakar leads the effort in Zero Energy Networks Laboratory, that's ZenLab, at DESC IISc, where his team works on building embedded electronic systems for application areas such as airplane cabin, industrial IoT, air quality, tactile internet applications, autonomous drone charging systems, machine learning, and AI for IoT applications. We welcome you, sir. Over to you.
Thank you. Can you hear me well?
Yes, sir. Perfect.
Super. So what I'll do is I'll spend some time on 15.4, IEEE 802.15.4 fundamentals, and then I'll move on to 15.4e, which is another important extension for 15.4, and from there we will take on the actual work that we have been doing and sort of entice you into the implementation details of some parts of what we have done. Okay, so just to give you an idea, this 802.15.4 is, if you know the OSI stack very well, the 15.4 is actually at the MAC layer. Okay, and this is the PHY. And like Ethernet, which has also defined in the MAC and PHY layer, the 15.4 is also defined here. Now, the application on top here essentially is uses an API which is called from a association called ZigBee, group of a consortium, industry consortium, and that's when ZigBee came into force and they started using 15.4. Now, quite like the application of ZigBee to 802.15.4, so I'll write here as 15.4. You can also have situations where ZigBee could be not the one, but in fact, the industrial Y-HART can be the other option.
Sir, sorry to interrupt you.
Yes.
We are not able to see your screen.
Not able to see my screen. Okay, I'm started to write. Let me share again then. Yeah, this should come up now. Let me see. You see it now?
Yes, now we can see.
Okay. Yeah, that will be great to interrupt. There's no issue at all. Please do interrupt. So let me write it all over, and so that the continuity comes up. So what I was trying to say is that the whole thing actually operates from the MAC layer on down below. This is the MAC. This is the PHY layer, and the PHY layer and the MAC layer together are defined in 802 IEEE 802.15.4. Okay, the extension for 802.15.4e, which I mentioned, does not change anything at the PHY layer at all. It remains intact. This is important. 15.4e, so I'll just call it 4e, is an extension of the basic 15.4. In other words, there are what are known as MAC behaviors, and this is one type of MAC behavior. I'll call it MAC behavior, and there is another type of MAC behavior which is 15.4e MAC behavior. Okay, so essentially the behavior changes, the PHY layer is the same. Now, if you look at ZigBee, ZigBee comes right on top, and ZigBee exploits, it's a consortium of industries which came up with the standard, and they said that they'll start using the same MAC and PHY. Okay, and that's how ZigBee is interchangeably used for 802.15.4. Actually, it's not true. The whole thing together, it is tightly tied to this MAC and PHY layer actually. Okay, now you can also have a situation where ZigBee need not be the one that is exploiting the lower layers. It can be also the industrial wireless HART, highway addressable remote transducers. Okay, Y-HART. Okay, there used to be a HART, which is in fact very popular, and that got replaced with nowadays everything is wireless, so it's replaced with Y-HART. The wireless HART actually uses the MAC and PHY, but with the difference that it does not use 15.4. So it's not 15.4. It uses 15.4e. So here are some very classic examples. So Y hat goes in this direction, and if it is Zigbee, it goes in this direction. If I rub it this way and write it here, it goes in this direction. Okay, clear till now? And why are we studying this? That's the question really. Why should we study 802.15.4 or 15.4e? Because it is a very ultra low power wireless MAC, really ultra low power, and it gives you decent data rates, and something like 250 kbps or so, and very reliable, extremely reliable. And how the reliability comes about, I'll show you. When you start using this system, so that's a major advantage, and its application area has been quite a bit. Okay, and it's I would say one of the vast application areas that you can ever think of, starting with retail, then going into medical, and industrial particularly is a very popular area where it is applied. Now here is another twist to this 15.4. This is MAC is clearly the same for 15.4. This is one MAC behavior MB1, and MAC behavior 2 MB2 is for 15.4e. The file layer is interesting. It operates in multiple physical layer, in multiple frequencies. There is an operation at 868 megahertz. In other words, a sub 1 gigahertz range. There is an operation in 915, depending on whether you are in Europe or US. You'd be using either 915 megahertz in the US or 868 megahertz in Europe and India, and also 2.4. This is 2.4. So it will still be the same MAC behavior, either MB1 or MB2. In fact, it's just not limited to MB1 or MB2. There are MB3, MB4, MB5 as well. Okay, so it's very, very flexible, this particular 802.15.4. And in fact, the E extension, you have to be very careful when you use the word 15.4 E extension. You can write 802. So let me write it well, although it's not all that convenient to use this here, but 15.4 E, you should say dash TSCH. You should be very careful. You can also have LLN. Okay, you can have something else. You can have something else also. Okay, I'll show you the paper where all these things are defined. So be very careful about the MAC behavior. So this is MB2 from what we just did. This will be MB3. Okay, this will be MB3. It will still be 15.4e, but it will be MB3. You can have an MB4 and so on and so forth. So you have to understand that it's a big standard, well matured, and absolutely wonderful to choose. And it is in the usual 2.4 gigahertz ISM band. And it gives you multiple channels for you to work with. I think there are 16 channels which you can use. The whole frequency band is divided into multiple channels, and I think each frequency is each channel has a bandwidth of 2 megahertz, okay, and so on. So these are details which you can easily pick up. So I don't want to spend much time there, because if you pick up, if you Google, you will find that. I'll show you some interesting things about this particular MAC, and that's where perhaps it might be useful. See, this particular MAC actually can operate in two ways. One is it can operate in CSMA, CA. This is channel access. Okay, I'm now switching to channel access. Channel access can be CSMA, CA, or it can be time slot, or what is known as beacon enabled. I won't even call it time started, I'll simply call it beacon enabled to begin with. Beacon enabled. Okay. This I'm sure most of you must have studied about the carrier sense multiple access collision avoidance, where you have multiple wireless nodes trying to access the medium, and there is a contention mechanism, which is this CSMA, and one of them wins it, and the remaining ones have to wait until the transmission is completed, and then they can come back and look up if the medium is free, and so on and so forth. Right? There is it's also the same thing that you actually do even in the Wi-Fi world. Anyway, so that is on the one side. The other side is to know a little more about how you can actually do CSMA. Here, there are two things. I think this is useful for you in this course. One is you can do energy detection. Okay, you can do CSMA based on energy detection. The other way you can do is you can do carrier sense. Okay, carrier sense. So when I say energy detection, you may actually have to plan a little bit more carefully here. Okay, so let me get into that detail. Let's say your receiver sensitivity is minus 85. Let's say minus 85. Yeah, let's say minus 85 dBm. Okay. You can decide that you can now use this parameter. Actually, this will be specified in the radio. Whenever you buy the radio, you'll get this number. If your receiver sensitivity is minus 85 dBm, and you find that when you switch on your RX, okay, RX means the receiver. So I will go in this direction. This is the antenna which is receiving the energy. This is the mux, which will switch between RX and TX, and this is the chain for, let's say, the RX chain, and this is the TX chain. Okay, and here what will you have? You will have a low noise amplifier. And I'm just writing a very rough picture. Okay, so don't catch me on the detailing on this. Okay, here you have a low noise amplifier which is receiving the signal. This is a mux, because these are mostly half duplex radios. They have to shift between either transmit mode, or this is the reception mode, and this is the transmit mode. So once you switch on the state machine to get the data in the reception mode, you see the energy on that system. Supposing you find that it is at minus 60 dBm, your receiver sensitivity is at minus 85 dBm. So you are, let's say, I'll make it for ease. I'll make it this at 65. Okay, you have a 20 dB. You have an energy which is 20 dB higher than the receiver floor. Clearly, this indicates that there is someone transmitting, because when someone transmits, you will have a higher energy, right? And if your LNA sees something close to minus 85 dBm, you realize that you are the medium is free. So this is how you would do energy detection, clearly indicating that this is the medium is free. The other way is to do carrier sense. Okay. Carrier sense is also very similar to ED, except that you are going to verify whether the frequency channel is available to use. You're just narrowing down. Okay. Is available. In that case, you may actually do an energy detection across all channels. In this case, you may do specific to this channel. I'll tell you what this actually means. This means, supposing you're on a particular channel, and this is 2402 to 2404, let's say, this channel. I've just taken some randomly 2 megahertz channel. Okay. In this, I'm sitting on this channel. I'm interested in knowing in this channel if there is any other Zigbee / Wi-Fi / whatever transmissions. I'm interested in this. Now, if it is Wi-Fi, I don't care. I might declare that the medium is free. But if it is Zigbee, I may not want to do a transmission. So that question still now? Am I going too fast? Folks, if there is no feedback, I'll have a difficulty. You want me to start the video to show my face a little bit? Folks, any questions? Preetham, are you there? Preetham?
Yeah, sure. Yes, sir.
Yeah, I just wanted to check. You're there, right?
Yes, yes.
Yeah. So any questions? How do I see the questions on the, is there any chat box which I can open right here?
Yeah, there is a chat option window. Right now, so far there are no questions. If there are some, then I will alert you.
Yeah, you can stop me, Preetham.
Sure.
Yeah, and I hope it's going okay there. Am I going too fast, Preetham? It's okay?
I think you are going at the right pace. So you're explaining
right,
the basics.
Yeah. Thank you, Preetham. Yeah. Okay. All right. So let's move on. So you see now there is a slight difference, right? You may want to do energy detection without caring about whether you are interested in Zigbee, Wi-Fi, or whatever. You just say 20 dB above. Okay, I'm going to declare that it's gone. I'm not going to do any transmission. That is simple energy detection. Now I may want to do a little more cleverly. I may do carrier sense. In other words, I may want to know the type of technology type which is actually doing a transmission. I may declare that I'm not going to transmit if I find a Zigbee, and I may declare that I'm still okay to go if it is a Wi-Fi, because you cannot avoid anyway interference from other technologies in the same ISM band. Okay. Here, another important thing is an indication. How do you do an indication? What kind of indicators are available in this standard? There is one nice indicator called LQI. This is called link quality indicator, and this indicates the quality of data packets received by this. Essentially, the quality of data packets. So I don't have to elaborate, but I'll still write it. Quality of data packets that are received. Okay. And the received signal strength can be used as a measure of the signal quality. That is, anyway, you can do that. The RSS is a measure of the total energy of the received signal. The ratio of the desired signal to the energy, to the total in-band noise energy, is another way of judging the signal quality. Okay, so you can use that also. So the link quality can be also judged using both signal energy as well as the signal to noise ratio. Both you can use. Okay, so these are some nuances in the LQI, and you do LQI on a per packet basis. This is very important. Okay, unlike RSSI, which is collecting some symbols and then averaging it, you do this on every single packet. Okay, and it is reported back to upper layers and so on. Okay, this is one part. Now, how do you assess whether a channel is free or not? Again, there are three modes in this whole thing. There is something called CCA mode 1. Then there is something called mode 2 and mode 3. In mode 1, you now learned about energy detection and so on, right? So somehow you have to use this, and you must get the 15.4 MAC to sort of get configured to use these things that we learned, right? Either it is carrier or whether it's ED, energy detection and all that. So in CCA, what you do is you only take ED, energy detection. Only ED is used. You declare whether the channel is free or not based on the simple ED. In CCA mode 2, you do carrier sense. Quite simple, because we learned that just now. So you consider only CS. In mode 3, it can be an AND OR of ED and CS. Again, pretty straightforward, right? It can be and/or, both can be either one of them. So you may want to choose. I think the flexibility of this and or is actually given to manufacturers. So if you want to do and, you can do and. That is, you take both and you declare. It's a very hard thing to declare it that way, but you'll be sure that the channel is free. You may want to do or also. So that's also another possibility. So these are some important things in the 15.4 system. Then, of course, what is important is there is a packet format for MAC, and the MAC layer actually provides you a certain set of interfaces, and you must follow those interfaces, and you must follow the MAC protocol frame format. Okay, so as I said, there are two ways of doing it using 15.4. One is you can use, you can put all the nodes. Basically, it will start with the PAN coordinator, personal area network coordinator, and then there are nodes all over. Okay, there are nodes all over. Sorry, let me write it a little more with rigor. Okay, you can have transmissions, you can have many of them. Almost overlapping this, you can have, so this is the PAN coordinator. Almost overlapping this, you can have one more PAN coordinator. Okay, maybe it's co-located, there is no problem, provided the frequency that you have set on this, call this A and call this B network. As long as A and B networks are frequency separated, you can configure them, you can co-locate them. You can co-locate both these systems together. This is one way of doing it. The other way of doing it is you can go and actually say that this is a bit chaotic, right? If you look at this, each node has to contend for the medium, has to do CCA mode 1 or mode 0 or mode 3 or any one of them, 0, 1 or 2. Any one of these modes has to declare that the medium is free, ask for resources, and then do a transmission. And of course, before that, it has to know to which PAN coordinator it has to talk. So the PAN coordinator is known to it. It is security is all assumed. Okay, I'm just assuming that security is part of this because it does support encryption of it uses AES, so it's a symmetric key that is used. So that I'm assuming that it is very secure and all that. The network essentially will connect. The nodes will simply connect to the PAN coordinator, and then they do this transmission to the PAN coordinator. Okay, so this is one way of doing it. The other way is you don't want this chaotic situation. You want things to go in a guaranteed time slot. Okay, so then came this notion of GTS, which is called guaranteed time slot. And let me take a little thicker pen so that will help. Yeah. So the GTS is interesting. What it does is it gives you a frame format. You can switch the same MAC to 15.4 MAC from normal mode to GTS mode. Okay, so in that, what happens is there is a cap period, contention access period, followed by GTS slots. Okay, you'll have some number of GTS slots, and then there is an inactive period. Inactive period. I don't see why this should be capital, so I'll make it small. Okay, here this is the beauty. This is good, right? You can get hold of guaranteed time slot. Let's say this GTS, you are interested. I'll just divide this into smaller chunks, okay, so that this is 1, 2, and so on. You may get one slot for yourself. Or let's say node 1, this GTS is fixed. So every time there is a beacon, this is the start of the beacon, this is the end of the beacon. maybe there is a small delay before which the second beacon starts again. It starts again here. This, so again, when it starts, exactly at the same point, node 1 can do its transmission. Okay, I have assumed that as usual there is cap, slightly bigger one, of course, cap here, and these are the different GTS slots, and the node gets the slot, I mean the time slot all over for its transmission. Now the point is, if it wants to get to this and get a reservation of a slot, it has to first contend, because how do you bootstrap? You have to get nodes to contend, it has to win, and then the PAN coordinator will say, okay, now you can go on this slot and you can start your transmission. Now that can be an eternal merry-go-round. You may keep trying, but you may not win the slot, and you may not win the medium, and you may not actually get a slot. So there has been a lot of active research about how to reduce that and how to ensure that in quick time there is access to the availability of a slot, reservation of a slot. There is one more peculiarity of this system. The standard actually says, if you read carefully, it does not give you any indication of when you should throw this node out of the network. Once you get access to the resource, you can keep it for lifetime in a way. Unless there is no activity, the PAN coordinator has no choice but once it is allotted, it's done. You cannot do anything. So node 1 may actually have no transmission, may actually have no sensor data to transmit, but it will simply hold on to that resource because of the fact that it won the medium and got the slot. So that is an issue which again researchers have found some ways out of how to kick these nodes out of the network. And in fact, if they win only for that super frame, and then they'll have to contend all over for the next super frame. This is super frame 1, this is super frame 2. They'll have to win all over again in order to get access. So this is not guaranteed. So this cannot be node 1. I'll put a question mark because nobody knows how long or how much they can win this system. Okay. Then there is some interframe spacing I mentioned to you here. That interframe spacing has to be maintained, and then you do what transmission. Okay, this being a wireless technology, it has its usual problems of hidden node problems and exposed node problems and so on. So I'm sure several of you are already aware of that. So I won't go into the detail. Okay, so this is what I wanted to tell you about what 802.15.4 is all about. We will now switch to 15.4e so that we can understand a few more things in 15.4e, and then I'll actually show you the actual implementation of the 15.4e, basic implementations that we have done. Okay. All right, so I'll stop sharing and I'll take you to another document which will sort of help you to how do I unshare? Stop share. Yeah, there's a stop share. Okay, great. All right, so let me take you this. Yeah. Okay, now let me share again. Go back to Zoom and screen share. Yeah, this one. Okay, folks, do you see my new screen?
Yes, we can see your window.
Yeah. The window where the paper from Sister is there. Sister,
yes.
Sister. Yeah. Okay. See, folks, one option is to give you a lot of slides and make a super material. The other is to actually point you to some outstanding material that I have been reading myself and share whatever we have been doing so that you can also pick up from there. So this is my approach. This paper is about 15.4e in a nutshell. Okay, and I'll tell you why this is a very important MAC behavior and why you should know given that you know a little bit of 15.4. Let's skip all this. I marked a few sections, so I will go directly there. Okay, so this is about this one. See, the thing is, 15.4 did not do all that great. Okay, but at the same time, it had some plus points. Now here, overall 15.4 or 15.4e or whatever tries to now achieve certain very energy efficient communication, particularly in the industrial environment. So it will give you some sort of quality of service in terms of reliability, timeliness, and robustness. And the world is moving towards IIoT, isn't it? The industrial Internet of Things. Here, the industrial domain and the emerging CPS systems for low power, low range, wireless, robust wireless communication has actually prompted the growth of 15.4e. And believe me, this 15.4e is only 5-6 years old now. And it is something that you have to sort of get hold of, or in terms of have a grip on it, so that you will be able to design systems using the 15.4e system. Now, what is it? It's no magic. It is nothing but an enhancement of the basic 15.4 I mentioned to you already. And I also told you about the MAC behavior. Now, one such MAC behavior is DSME. And one such, another such MAC behavior is the TSCH. And another such MAC behavior is the LLDM. And one more MAC behavior is the TDMA. So folks, be very careful when you write 802, IEEE 802.15.4e. When you say, you put a dash and then you say TSCH. Otherwise, strike it off and say DSME. Otherwise, strike it off and say LLDN, or write TDMA, and so on. This is very, very important. And today, what I'm going to talk to you is none of them, of the ones that you see here, except I'm going to cover in detail about the TSCH MAC, because that is what we have been working in this project with us. So we'll talk to you about neither DSMA or any one of them, but indeed the TSCH system. Okay, clear? Now, when was this incorporated? You can see mid of 2016. Okay, so it's very recent. And implementations are just coming up now. And hopefully IAC's implementation will also be out there. And the grand plan is to have our own MAC there. Okay. Now, there are several issues open for investigation here when you build such a MAC. Including analysis of the protocol itself, then under different settings, then scheduling of flows in time frequency domains, delay bound analysis, to name a few, and so on. Right? See, here you have to note one thing. If you look carefully, if you look at TSCH, it's called time slotted channel hopping scheme. And then there is one low latency deterministic network, LLDN. Okay. The point is that the TSCH is also called a deterministic MAC, but you can't call it a low latency MAC. This is important. Please differentiate between the two. It is deterministic because you know when you will get access to the channel. To that extent, you are deterministic. But to say that you get it, let us say, every 1 minute, it does not mean low latency, because if your application requires a 10 millisecond actuation, a 1 minute access to the channel is not going to help you. Therefore, be very clear about deterministic MAC and low latency MAC. And that is where you will have to differentiate between TSCH and LLDN. LLDN is something interesting. It says that I'll give you low latency. Actually, you can, it's like a knob. You can program what kind of latency, low latency you need from your system. Yet it is, if it is low latency, also it need not mean deterministic, but LLDN combines both. It says I'm also not only low latency, I'm also deterministic. Okay. So let's not read every line. I'm just trying to give you an overview. Okay, then we move on to the time critical behavior of these MACs, which is something that the paper talks about. Okay, now 15.4e. Now, there are several applications, as we know, voice, video, and all that. There are trade-offs also. That is, you're looking at throughput, latency of these systems in terms of, because these are all high bandwidth, particularly video is a high bandwidth application, right? Wireless sensor networks usually do not impose any restrictions on what is the bandwidth and so on. But you can't be talking about, because when you say wireless, you more or less assume it is untethered, right? And that means it is either battery operated or it's a mobile device and so on. So therefore, energy consumption is a very important aspect. In fact, we all have experienced that, because our mobile phones are indeed one sells over the other because of its good power management schemes, and therefore that is important too. That is one thing that will come directly when you talk about wireless networks. Energy will be an important. Okay, now he goes into the details of 15.4. I will skip this because I already mentioned, except that the PAN coordinator is also given another name called the FFD. It's called the full function device, and it's called that way because it has more capabilities: routing, association, association and formation of a network, and so on. It does several nice things, and it has all the capabilities. Full-blown capabilities are available on the full function device. Whereas RFD is intended for applications that are simple. They could be end nodes. Essentially, RFDs are end nodes in the system here. So that he talks, and then I mentioned to you about bandwidth and all that. I don't think we should spend time here. I did mention to you about the two modes. One is the CSMA-CA based mode, and the other is the GTS mode. Here he's talking about the super frame and the GTS mode. You can see the same picture that I drew is out here. So there's not, it's all, I would say, duplicates. Now the 15.4e gives you enhancements to that 15.4 and gives you very good performance. 5 MAC behaviors. I'll skip all this because we know several of them now. But these are very important. These bullets are very critical, and let's spend a little time here. One is multi-channel access. Okay, this is something outstanding and something that is unmatched with what 15.4 gave you. So let's see what actually it means is, if you look at the old 15.4, there was no question of multi-channel access at all. Single channel is, I also showed you about a picture where PAN A and PAN B, network A and network B were co-located, and they were happily working by themselves just because they were fixed to a given frequency channel, and they could coexist because they are anyway frequency separated. That's not the case anymore. You can't do single channel communication because you're restricting the whole system. You want to accommodate large number of nodes without contention, and therefore deteriorating network performance is an important criteria, and you don't want that to happen. Delay and throughput are also important, so you have to keep all this in mind. 15.4e actually says, great, I don't want to do that. I will come out of it. I'll support multi-channel operation, and it says that I am going to do it with channel adaptation mechanisms. I will do channel hopping. I will not remain on a single frequency, and I'll use the full band that is available. After all, you are wasting the full, there are 16 channels in 15.4. If you co-locate 2 networks, you will choose one channel for one, another channel for the other. What happens to the remaining channels? You're just losing out on any good, let us say, utilization, because they are all not being used at all. So that's a problem. So channel hopping was brought in straight away into 15.4e, irrespective of whatever be the MAC behavior. This is important, okay, because we are now discussing the important changes that have come to 15.4e and not specific to TISH alone. The second improvement that came about is the information element, and this is unique information elements have come. There is a concept which was already there in 15.4, but it's extended now. Unique IE have been introduced to support various MAC behaviors. So you actually know what type of MAC behavior you're using by just looking at the IE, because the file layer has not changed. Please note. So you have to somehow be able to differentiate between them. So that's essentially what he's writing here. Okay, the IE of TSCH does not incorporate superframes, multi superframes, or group acknowledgement specifications, but it carries relevant information such as time slot length, time slot ID, or channel hopping sequence, and so on. So moment you know your IE, you identify the IE, you know what all are the features of that MAC behavior, and you only look for them, and that's a nice thing already. In a way, it is like multiplexing in the same frame different types of MAC behaviors. It's essentially that. Then the third bullet is low latency and low energy. I already mentioned to you that 15.4 or the beacon enabled modes are insufficient in terms of latency support. You didn't ask me why beacon enabled is not bad. None of you asked me that question. Folks, none of you asked me that question. You want the answer or you don't want the answer? Why the beacon enabled mode of 15.4 is a bad idea? Folks, anyone? Can anyone speak up? It's becoming one way.
Is it because, sir, collisions are possible or something on the channel?
No, but collisions will happen in the other mode. No, in the other mode you will have collisions. This is beacon enabled mode. I'm talking of 15.4 beacon enabled. There is no collision. Only in the contention access period there can be collisions, because that is the time when you are trying to get an access to the GTS slot. That time there will be collisions. But once, let us say, in a steady state, all nodes have got their GTS slots, there should not be any collision. And after all, it is beacon enabled. So periodically beacon will come. Put, it will keep coming. And once the beacon comes, you know where your CFP starts, that is contention free period starts. Within the contention free period, you know where exactly your slot is. And there you push a transmission. Why should that be a bad idea? It's also in a way, shall I say, it's deterministic, right? The problem is not there. The problem is the number of GTS slots. There are very few, folks. Very, very few, folks. It's under 10. Please figure out. Okay, if you read, you will know that the number of GTS slots are very, very few. In fact, you have, I think, only 7. There are 7 GTS slots and 9 cap slots. So it's abysmal in terms of support for large networks. You want low latency, low energy, but you want to support hundreds of nodes. That won't work with 15.4 anymore. And you can think of that also as another motivation for doing it this way with 15.4e extensions, irrespective of the MAC behavior. Okay, great. The 15.4e allows devices to operate at very low duty cycle and also provide deterministic latency. See the word here, please note, you have to deterministic latency, it says. Okay, so this is very important. It is deterministic. It need not be extreme low latency. No, it is deterministic latency. You know when you will get access to your channel. That's the point. Then there are other things, which are out there. I didn't mark everything. The receiving and transmitting devices coordinate with each other to reduce the overall transmitting load. See, the way you do it is, if you have tight synchronization between the transmitter and the receiver, you will ensure that the you can either do ACK-based resynchronization, or you can do transmission-based synchronization. Both are possible. Receiving and transmitting devices coordinate with each other to reduce the overall transmitting overhead. RIT mechanisms are used for latency tolerant applications. So he's also telling you that you need a little leeway. Don't do ACK-based. You can do ACK-based if you have a little leeway, but other ways you should perhaps do only with respect to the transmission-based synchronization. Okay, so all these things are mentioned there. Now, multi-purpose frames. This is amazing again. The frame formats of all the MAC behaviors in 15.4e are based on peculiar features of MAC behavior and its targeted applications. So you have DSME doing it in one way, TISH doing it in another way, and so on. So that's very, very important. Enhanced beacons. Yeah, you had 15.4, you had beacon enabled super frame structure, but that's insufficient. You have something called enhanced beacons in the 15.4e. Okay, and the enhanced beacon is a revision of the old beacon that we used to know in the 15.4 world. And this beacon provides great flexibility. Okay, particularly TISH MAC behaviors use this extensively. And EB can be differentiated from the legacy one, legacy beacon, by the frame version information issued by the PAN coordinator. You will actually be able to find out whether it's the old beacon or whether it's an enhanced beacon. And TISH and all that actually carry a lot of further information about low energy capabilities of the whole network. It also carries information about channel hopping, because we said that's an important requirement for 15.4e systems. So all of that. So MAC performance metrics are also important. Okay, so this is another thing. See how good the MAC is performing, the file layer is performing. The MAC may actually not know anything. For example, if you look at this MAX frame trace, I marked it here. This is an important link which goes to the upper layers. The upper layer, which is actually, if you talk about the file layer, the information from the file given back to the MAC in turn giving up to the application layers. So the MAX frame retrace is something that applications may want to use and say, hey, let's see, I think the link is bad. We need to do something else in order to ensure that this packet goes through successfully to the other side. So you can use these kind of levers, which may be useful for adjusting the, you may want to trade battery energy with reliability and so on. So that's a very important feedback information out there. So number of retransmitted or transmitted frames that require one or more retries before an acknowledgement, all that information you can feed. Useful information, lot of analytics can be done by application layer to decide what its strategy should be and how it can improve the MAC performance. Fast association, that's another important requirement for 15.4. It should not take several minutes to join the network. There should be some way of, in spite of getting to access the deterministic latency part, that is for data transmissions, joining the network should not become a big bottleneck. There are a lot of papers out there, folks. Again, if you are interested in this area, a lot of papers out there on joining time, how to fast join the network of a TISH system is well researched again. And of course, it's a ongoing area of research. If you are interested, you can look up papers in that direction. Group acknowledgement I did not mark because that is not something that the TISH MAC actually supports. So I didn't do that. Then there are other nice things about this TISH MAC. You may want to read this paper as thoroughly as possible. DSME is also mentioned, so let's skip it. Then let's go directly to the MAC behavior of our interest. And that MAC behavior of our interest is indeed here. Okay, this is TISH. So let's go here. So now I hope you are clear. I came from 15.4. I gave you an overview of 15.4e, the different MAC behaviors. I told you why 15.4e is important, the 4 bullets that we read up. And now we said, okay, forget about all of them. Let's narrow down and look at TISH, and only TISH for the next, hour or so. And let's see if we understand this better and we see the implementation of this better. Now, folks, this paragraph is critical for you because it says, look, all that is all fine. Where do you think TISH should be applied? Okay, here he gives some examples. actuator networks in oil and gas industries, which are defined as safety critical. Okay, it can be easily applied. High reliability and time critical assurances. It's not about zero latency and all that. Wherever time critical assurances are required. Folks, if you come from the industry background, I can tell you that PLCs are ones which the programmable logic controllers are the ones that are vastly used in process, right? In any process mechanisms. There is a schedule, and the PLC is programmed to follow a particular schedule. And every time it goes from one part to the other part, it may do some sensing and then report back. Say that the pressure here is so much, or the temperature there is so much, and so on. Depending on, everything is time slotted, and in each time slot it does some specified action, and it does this repeatedly and repeatedly and repeatedly. That's why it's called the programmable logic controller. And that means it is programmed to do it in a particular time sequence. It isn't that you preempt and confuse the system there. It is doing it in a particular way. That's how processes actually work, because they're all sequential. Sometimes several things are sequential. So you have to do it that way. This guy, dish can be applied there very nicely. You want to put a sensor, you want to pull off something from the oil and gas infrastructure networks. There you can apply dish in a nice way. And it does support channel hopping. They call this frequency hopping mechanism. Greatly improves reliability. Why are you just sticking on to one channel? Why don't you use all the channels out there and use them very effectively? That's how the reliability has come in here. And Tish allows you not the kind of paltry 7 and 8 nodes which 15.4 time this GTS based mechanisms actually supported. This you can go to very dense network. Okay, and you can build a large network. You can build number of nodes can be there, and it really scales very well. Okay, and at the same time you can maintain stringent time slots, time constraints using fixed length time slots and all that. It also supports multi-channel access. TISH uses this slot frames, thus facilitating the collision-free communication. So what I'll do is, this is all very cryptic for you. So let me go back and stop sharing, and I will show you a picture which I'll write by hand. Okay, so how do I stop sharing? Stop share is here, and I can share again. Yeah, I can share, go back to Zoom, and I can share again. Okay, yeah, I want to share this guy. You see my whiteboard? Do you see my white screen? Whiteboard? Folks?
Yes, sir.
Okay. See, basically, Tish is like this. Think about this picture only. This picture and nothing else. Okay. This is F, frequency. This is time. You just divide them. Don't pardon my drawing because it's not all that great. It's just this, nothing else. Okay. Let's say A to B is communicating here. Now this and this. This is a time slot. This is a slot frame. This is a slot frame. Okay. Just remember this much, folks. Everything else will fall in place. This is a time slot. I call it TS. This is another time slot. Unfortunately, I didn't draw it in equal, but pardon my error. Then you repeat all over. Okay, you repeat all over. So if someone transmitted here, let us draw the picture again. Somehow it may go and do here. That's possible. Or it can also do here. You can just rub it and put it wherever. Okay. Now, what is the game? Game is pretty straightforward. You must, the PAN coordinator must tell when it switched on. This is the place where it switched on. This is switch on. Okay. How long was this from the time it switched on? It should tell the time. It should simply say, I switched on here, and so many numbers have passed by. How many numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say a new node wanted to join here, just as an example. It cannot obviously join here because the beacon comes here. The beacon comes here. So it has switched on here, but unfortunately it can't do anything here. It has to do at the end of, it has to listen for a beacon, right? Enhanced beacon, which contains all the information. Let's say this is this one here. You get back this. So this guy will wait till this long, and he comes up and gets this beacon. Once he gets this beacon, what should the beacon information contain? It should say, when was it switched on? This should be on. This should be available. So you actually know the time at which the whole network was up and running from the origin, from there onwards. And then you have some sort of a very simple formula by which you know. Actually, you can count, right? I know the current time. This is my current time here. This is my current time. And I know when it was switched on. So I know how much time has elapsed. And I also know how much is each time slot. I also know this. Quickly, I can make out everything, and I know that, oh, I'm right here. So many slot frames have passed, and now I am in the beginning of this time slot. And then it will get access to some particular channel, particular frame in which it can actually start the transmission. It has to figure out these things essentially, and once it figures out, it has joined the network. So once it has figured out, it will join the network. Once it joins, it knows from there onwards it is synchronized to the network. And if it is synchronized and it knows how to hop the channel, because as I said, F is on the y-axis is F, frequency. Okay, this is frequency channel 1. This can go up to 15. Okay, there are 15 channels in 15.4e. 16, sorry. Sahana and Sita are here. They correct me. There's 16 channels. There are 16 channels that you can go, and your slot frame can be defined by the PAN coordinator. You have too many nodes. You expect too many nodes in the network. Get rid of this line. Simply get rid of this line and join everything. And you declare that your slot frame length is big. That's it. Okay, you put your line here now. Put it here. So you see, but of course you have to plan this out, right? You have to do it right in the beginning. You can't say that I will do it on the fly. That's not going to work. You have to a priori determine what your network size is going to be and how you want to plan the whole thing out. At least to begin with, you don't want to complicate. You want to keep it to some limited size and plan it based on the number of nodes that you are likely to connect to. So then you are given a channel, and from there onwards, you know how to hop. You know the hopping sequence. You know the hopping sequence. Okay. If there is a node network like this, there is another node here. There is another node here. There are two nodes connecting to this, let's say. This node is now like a receiver for two other nodes. This is A, this is B, and this is C. Now, when A wants to communicate to C, C will have to sit on the same channel as that of A. Okay. And when B wants to communicate to C, C will have to sit on the same channel as that of B, which means C will have to maintain two schedules. And that two schedules will be running. Of course, it will have to be time interleaved. Otherwise, it can't be in the same at the same time on both, right? It cannot do that because it's a single radio. The receiver is a single radio. It can maintain this time schedules and receive data from both of them. C to B, the sequence is known. Channel hopping sequence is known. C to A, the channel sequence hopping is also known. And that's how the whole network starts hopping so that it can battle interference and it improves reliability and so on and so forth. So this is a basic idea. I will stop sharing and I'll go back to the document so that you can connect easily again. Okay, now that is this. I go here and then I share the screen and yeah, this document. Okay, folks, you see my document? Do you see my document?
Yes, sir.
Okay. So, folks, now it's very easy for you to follow this document because it will tell you everything that we just spoke of. All right. So now you will listen a little bit from Ipsita. She's here with me and she's part of the team, and she will tell us a little bit about. Okay, let me before I hand over, I'll tell you about the slot frames. As I mentioned to you that this is how the slot frame structure is. You just call it absolute slot number 1, absolute 6, 7 going on, right? It's from the time the system switched on, it is just counting upwards, and that's I think what they wrote here. I didn't mark it, but I think we can figure that out. Let's see. Slots, communications, and all that. Every time slot accommodates a transmission and an eventual acknowledgement. Here, if you look at this figure 17, shows a time slotted super slot frame. In this example, the slot frame repeats every 3 time slots. Let us take 3 devices A, B, and C. In time slot 0, device A transmits its data to B, and during 1, B transmits to C, right? During time slot 2, the devices remain in an idle state. Okay, that's also shown there. This repeats in the same order for every 3 time slots. Now, this sentence is nice. Every time slot in TISH PAN has an absolute slot number, which increases globally and is used to compute the channel in which a pair of nodes communicate. And so this is now extended to concurrent slot frames and so on. So this is essentially the start of the network. That is where the absolute slot number actually comes in from here. Now coming to channel hopping, maybe Sita, you can elaborate a little bit on the channel hopping. Yeah, go ahead.
Good afternoon all. This is Ipshita. So basically, channel hopping is one of the main characteristics of TISH. There is a formula to determine the frequency at which each node will be transmitting its packets. The formula is basically f of ASN plus channel offset modulus of n channels. So ASN is nothing but the absolute slot number, and as mentioned in the paper, it increments globally with each time slot. And the channel offset is set by us, either it's 2.4 or 915 megahertz or 2.4 gigahertz. And then n channels is the number of channels we are using. So maximum we can use 16 channels, or we can restrict ourselves to 2 to 3 channels also. Now the F function is basically a lookup table which contains the channel in the 16 different channels in form of an array, and they can be arranged sequentially or in a random manner. So that is how we determine the channel hop in each time slot.
Great. Thank you, Shita. What happened to my slide? Yeah, see. What happened? The screen is sharing response. For some reason. I don't know. No, I'm not sure. Yeah, I think it's come back. Okay, great. So thanks, Ikshita, once again. So you see, that is what is mentioned here, and that's how nodes actually try to sort of synchronize and do this transmission. So there is this span formation also, which is an important requirement. MLME beacon.request is something coming from the upper layer. MLME stands for MAC layer management entity, and that's a beacon request which comes. Once MLME beacon.request comes, it goes down, and then the beacon is sent out, and then that beacon contains super amount of information. Now, what does it contain? The EB contains, this is very important, okay? So this is very important. It contains time information, channel hopping information, time slot information, and initial link information. Very important. So let me mark it for you. So these are very important. Now, what is time information? This provides specific time period at which the node should synchronize with the network. Time slot information describes the time when the data will be transmitted. And lastly, the initial link information gives the time on when to listen to an advertising device and transmit to the same device. So EB is critical. So it has all that complete information related to the time related information is carried there. Okay, so quite like that, devices can actually ask for additional slots. That is also mentioned here. And I think these are advanced things, so we can leave that. Fast association I mentioned to you is very critical. See, one of the things you can do is, as Ipsita mentioned, there are 16 channels. You don't need to use all of them. Why should you go y-axis F of all 16? Keep it 4, keep it 5. Now that is your choice as an administrator who sets up the network. So keep it at a reasonable number so that your slot frame and structure is designed well for the current network, plus a few additions that may come up in the coming months or coming years. So all that you should also make sure. So in fact, there is a MAC, there's a function in the standard called MAC response wait time, and which is used for the association process in legacy 15.4. It's coming from the previous ones. This efficiently reduces association delay. So you want to keep this, you want to use this to monitor the amount of time it takes to join the network. So essentially that is an important thing. And then of course there is time and node synchronization of the complete system. See, node synchronization is another useful part, because if a node has no data, it may just keep quiet. So that can relate to, that can be a risky affair. So you may want to periodically send out a packet called the keep alive period. There is a period over which you have to, the node actually sends out a small packet, and that's mentioned here. You can see node synchronization is also done to ensure connection with neighboring nodes in the slot frame based network. And if they do not receive a request from the device at least once per keep alive period, they will send an empty acknowledgement frame to perform acknowledgement based synchronization. So the synchronization is a big deal, and as I said, it can be frame based synchronization or ACK based synchronization, and it's very, very important here. Now this picture is actually telling you the issue of, just concentrate on the picture. Device 2 you take, okay? Device 2, if you see, has two arrows coming in, whereas device 1 has only one arrow. That means device 1 is only worried about itself, its coordination to PAN coordinator, whereas device 2 has to worry about its coordination to device 1 as well as to the PAN coordinator. That's what essentially this means. Let me see. Figure 19. Yeah, it says this. Take the example of network containing a PAN coordinator and 2 nodes. The PAN coordinator acts like a timekeeper of the entire network. Device 1 synchronizes to only PAN coordinator. Device 2 has no influence. The second device time has no influence over the time synchronization of device 1. That means you cannot, device 1 is not influenced by device 2 because the arrow, as you can see, is in this direction. Whereas the synchronization of device 2 is dependent on both of them, PAN coordinator as well as device 1. So essentially, it has all these nice things about frame-based and act-based synchronization and so on. So I think this will give you, has given you some idea on overall how TISH works. But before we close on this part, let us just look up the CSMA part. I want to ask you folks a little riddle here. Okay, the question is, if the whole network is time synchronized, where is the question of any contention, right? You may ask this question. Why should there be contention at all? And why should CSMA CA be implemented in a TISH network? Okay, if you ask that question, it turns out that you can do TISH and you can also do CSMA CA. You can have that slot frame structure and you can also do CSMA CA. In other words, you can do what is known as dedicated link. You can have dedicated link and you can have shared link. Okay, in the shared link is pretty interesting. Okay, the shared links are used to assign more than one device during data transmission. Okay, when a packet is transmitted using a shared link, it awaits for an acknowledgement. These links are prone to collisions and failures. That means you pick up one slot and you can assign, let us say, 2 transmissions at the same time from 2 nodes to a single, let's say, a parent. Okay, it's possible. You can still do it within that small rectangle which I showed you. But that is rare. But however, it supports. This is also a very, very important point that you have to know. But whereas in the dedicated link, you want to make sure that there are, the packet definitely reaches without any collision. Okay, so that's when you would want to use the dedicated. Let me just check this. The shared link and dedicated link. Shared links are used to assign to more than one device. That's what we said here. And these links are prone to collisions and failures and all of that. At this point, a successful transmission, the backup window is set to the minimum value. But whereas if you take the dedicated links, this is very important. More reliable there, no contention between nodes is to occupy the channel. In a dedicated link, the backup window does not change when the transmission is successful. But when the transmit queue becomes empty, the backup window is also reset. So you can use these little rectangles inside the standard in very interesting ways and very suited for several industrial applications and very useful to know how to implement this MAC, how to go into the details of this MAC into great detail. That's all I have for now in the first part. I will now go and switch over to the implementation part and show you how we did some sections of implementation, and I'll also show you some videos of our critical implementation parts. Preetham, how is it on time wise? Hello, Preetham.
Can you hear me now?
Yeah, sure.
Okay, sorry, I was speaking on mute. So we had planned 2 sessions with a break in between. So you can choose to give a break whenever you think it's a right time to break.
Okay, but there are no questions coming from the other side, Preetham. I would love to use this time to, sort of get some questions out there.
Yes, we would also like the participants to kind of participate in the discussion, because that's when it becomes more interesting. So all the participants, please use the facilities for unmuting yourself and ask the question. If you are shy of asking on speaker, then you can put it in chat and we can read out the questions. But please make it interactive. You would also gain much, and also we also get right feedback on what to cover and what not to cover.
So node-to-node synchronization means that nodes are sharing schedules of their transmission, of their active periods and active periods like that with each other. Is it that so?
Yeah, so active period and inactive period is a down and out kind of thing anymore. They don't use those terms anymore, because that's what was being used in the 15.4 world. In the TISH world, you talk about time slots, you talk about the slot frame, and synchronization with the enhanced beacon, and transmissions which are, you transmit based on where you are in the whole network, right? Suppose you have identified your parent, and you know that it has to go to that parent, and you should channel hop in a manner that your transmissions are successful. Number one, that's possible only if you do a tight synchronization. So essentially it is that.
So, sir, it means that you're sharing your schedules. Right?
Yes, of course. It's actually a distributed schedule. Essentially, the ASN is known to you, and you have a hopping sequence which is already fixed. After you got the EB, you got the ASN, you did some computation of the node computes itself, and it knows its schedule, and that it need not distribute that schedule to anyone, because it knows, moment it knows its schedule, it also knows its parent, it knows where in the network it is, who its parents are, and how successful this data gets transmitted to its parent.
Okay.
It's a bit strange, right? So how does this schedule how does it work in a distributed manner? That's really the beauty of the whole system. If I know the start of the clock from where it started, the way the 15.4e has been written and conceived is very interesting. You just use the ASN, and you know the number of channels that you have, and you know the hoppings. From there you compute the hopping sequence essentially, and you go up, down, up, down. Every time you go up, your parent also goes up, and every time you go down, the parent also goes. So they're hopping together in a way. I think we can show them a picture during the lab time that might clear some doubts. Yeah, that graph we can show. We'll show you some pictures, maybe that will give you some clarity.
Okay, sir. Thank you, sir.
Okay, then let's break for 10 minutes and reconvene at 3:30. We can do a nice demonstration from there. Ipsita, you want to add something? Sahana? No, it's fine. Okay. Preetham, then we will take a break now.
Okay.
So, and
then
we'll start again at 3:30, Preetham.
Yeah, that should be fine.
Yeah. How long should be the break?
You decide. It's like depending on how much time we
are okay. We are okay. Yeah, 10 minutes should be fine for us.
Okay, then we'll resume at 3:30 then.
3:30, yeah. I'll be online anyway.
Yeah. Thank you so much.
Just that I'll be on mute.
Yeah.
Okay, I think we should start now. It's a little past 3:30. Folks, shall we start? At least one of you can say yes. Unmute and say yes.
Yes, sir.
Okay, thanks. Can you see my screen?
Yes, we can see your screen.
Okay, very good. So, quick recap, why 15.4e over 15.4? This is an amendment, 2016, combats limitations of unbounded latency, power consumption, and so on. Effects of interference is gone because you are using the whole range of frequencies which are out there because of frequency hopping. Suitable for equipment and process monitoring, condition monitoring, predictive maintenance and diagnostics, asset management, and other industrial applications. Now, look at the limitations and look at the fortification. Unconstrained delay, you have time slotted access. Restricted communication reliability, TDMA and channel hopping, bringing in huge amount of reliability into the system. Interference and fading, again channel hopping coming to your rescue. Power consumption, nodes remain active only during their respective time slots. In any case, power consumption will come down drastically because of synchronization. But the cost of synchronization is often ignored. So do factor in that it is energy expensive to maintain synchronization. So take this word with a little bit of pinch of salt, that it's hugely, immensely, power saving, power consumption less and all that, because you can have a drift in the clock. So that problem is there. But in any case, it is definitely, it's an advantage. If you look at TISH components and implementation of TISH, okay, there are 5 major components that you have to worry about. One is the slot frame. The other is the channel hopping. The third is you use slot frame and channel hopping and create the network. And then, of course, scheduling. It could be beacon scheduling, it could be packet scheduling, and so on. And all of this tied together tightly with time synchronization. These are the components of the dish. If you implement these 5 components, then you have more or less implemented the complete 802.15.4e MAC. Okay, TISH MAC. Very important. TISH MAC. The MAC behavior here is TISH. That's important. Now, again, just to recap and give you an overview, what you see down below is the packet structure, right? You have the MAC header, you have the MAC footer, MHR and MFR. MAC header, MAC footer. The MAC payload is there. Information elements, we discussed this last time. It's out there. Header information element is there. Then you have the PAN ID, source PAN identifier, destination PAN address. Then the PAN identifier, source address, destination address, PAN ID, sequence number, frame control, frame payload, and FCS. If you are from the world of 80s and 90s, you quickly realize that this frame structure is called LLC, logical link control, because, or even if you take PPP, you will find that the frame structure looks very similar to point-to-point protocol. But anyway, LLC is what it is, and it is no, the frame structure you see is no different here. All right, so you can see that every time the 15.4e MAC stack, TISH MAC stack is energized, you have the packet, once it comes in, is delivered up using the up arrow there. On the left extreme top is the up arrow where packets go up. If you want to transmit a packet, you give it from the right side, go to CCA, all the 4 blocks which are important out there, TDMA, ASN, and then CCA, synchronization, and FDMA, and all of that. And then you send out, after you have fixed all these parameters, you send the PDU, and the PDU format is shown here. So this is in essence what it is. Now, the TISH critical MAC functions are here. You can see what I've shown on the right side. Forget about all what you read on the left. look at that shared link. Okay. Before you go to the shared link, look at the X and Y axis. The X axis is time slot. The Y axis is the channel offset. You could have gone up to 16, but we have only gone up to 5 here. Or rather, the picture is taking only up to 5. And you know what each rectangle is? It's one time slot. And you know one big block, how much it is? That is the slot name. And you also know what shared links are. In the shared links, you can see that B to A and C to D are provisioned at the same time. And that's when you may want to kick up CSMA CA and bring in that communication. Or you can also look at A to B in slot 1 and channel offset 0. A to B is communicating, and that can be CSMA CA, but it can be on a dedicated link. That means A may not want to decide to transmit to B if it is very noisy. May simply say, forget it. I know I got a good time slot. I know I can transmit to B, but I'm not at all happy because the noise levels are very high. I may decide not to transmit. So that's also possible. Okay, so this is the kind of a structure that you see here. You see on the right side nodes and how their arrows are situated and how the whole network is conceived here in this system. So I don't think we need to discuss anything on the left because the right side carries a lot of information already there. Folks, this is our implementation, and I would like to spend significant amount of time explaining this picture because we have actually implemented the 15.4 TSCH MAC, and I want to spend some time here. See, this project is a large project in which there are multiple partners, and we are not developing the radio. The radio is coming from IIT Hyderabad. But at the same time, we have to continue our development of the MAC, right? That's where we chose a controller. It can be any controller. We just chose NRF 52840. This is an ARM processor. And we bought this ADF 7242, which is a general purpose 5-layer system with a radio controller inbuilt into it. Okay, it has a TX buffer of 128 bytes and an RX buffer. TX, I mean transmission buffer, and an RX buffer of 128 bytes. What you see on the extreme right top is what we have actually implemented. Okay, you know that it starts with start. You're in idle state. Supposing you want to do a transmission, you go to what is known as the phi ready state. Phi ready is physical layer ready state, and from there you trigger to a transmit state. You do a transmission, and then you go back to phi ready state, and then you go back to the reception state if you are expecting an acknowledgement. So all of that will happen. So you go from here. Let me draw that. It goes from here. Then you go here, then you go back, then you go here and you wait for a MAC. Okay. This is essentially what you do if you are trying to do a transmission. And now it's easy for you to figure out several things. What I missed out is, while I said this in a trivial way, what should actually happen is what? It has to go from idle to phi ready. It will have to check if the channel is good, the channel is free, and if the channel is good, then it can go and do a transmission. This is what you would do if you are doing shared links. This is what you would do if it is dedicated link, all right, but you may also want to say that I will do CCA even in dedicated links. You would want to go and do this. So this in a way is something that will only happen during transmission. The reception, we need not worry about this part. Okay, and now this RC idle, RCTX, RC phi, and all of that, these are all offered by the radio controller of this guy. This one, this RC guy is here. So he gives you a certain API, and we program and call those functions from the left side, and we pass through a serial peripheral interface which is running at 4 megabits per second, which is called the SPI interface, and then we program this controller, and the controller then commands the radio to go from idle to fire ready to TX, back to RX, and so on and so forth. Okay, so that's the key implementation strategy that we have taken. I'll be happy to take questions if you have any here, because several things are hinging on the fact that this is implemented. Okay, you can stop me anytime. Now that's what I was telling you. The ADF chip that you saw previously actually has all of this inside, and this is another chip which is being developed by IIT Hyderabad. So we did not want to wait for them to give you back the chip, because anyway, once the chip comes, it can't be a sequential development of anything, right? You have to do parallel, you have to do how to utilize your time in an effective way. So we went and got this chip, and that's what our implementation approach is all about. Now let me show you the one little thing that about what actually happens with CSMA and CCA. Now this is a shared link in time synchronized channel hopping, which is mode where it's susceptible to collision. Collision leads to transmission failure, you know all of that. Now CCA is implemented to prevent transmission during the prevailing conditions of strong external interference. I did talk to you about mode 0, mode 1, mode 2, and all that in the 15.4 world. And how does all this play out? This is as per the standard. This is what you should do. Standard tells you do this if you want to do CCA. So what will it happen? It will start with MAC TSCCA offset plus this plus something gives you this time. MAC TSTX offset. Now there will be a certain time associated with it. There is no sanctity about this time. But if you fix it to some value, you must ensure that that value is acceptable to the receiver. That is very important. So you can also look up the standard and find out what are the typical, or I would say, yeah, that's the typical ballpark numbers which are associated with these things. You can actually see them out. So MAC TS TCCA offset, CCA, MAC TSCCA, MAC TS RXTX, and then you go on to do a transmission of the frame. I'm making an assumption that it is successful. So you are actually doing TX of the frame, which now has up to MAC TS max TX. This is the amount of time that you have declared. Up to that time, you can do a transmission, and after that, you have to give a delay, and then you have to wait for what? You have to wait for the ACK to come. So go and do your transition to MAC TS ACK and wait there. Okay, all of them have very special fixed boundaries, right? So it's all, you have to ensure that you do a super implementation of your timers. You ensure that everything is in the right state, so that when you do commercial testing between when you do testing with commercial systems, they are able to interoperate, and then they are interoperable, and they will still give you data. All manufacturers have to follow that, and that's why the standard is a very important thing. Okay, so any questions still here? This is just one example of CSMA CA, because CCA is something that you know well now because of what we started right in the beginning. And look at what happens at the reception side. All that you do in the reception side is shown below. Your MAC TS RX offset. Okay, you have here it was MAC TS CCA offset. This is MAC TS RX offset. Again, there is a certain time. Then you have MAC TS RX wait. Okay, then you wait. From here onwards, you wait. And then you have MAC TS TX ACK delay. Again, there is a certain time. And then you have up to MAC TS max ACK. You have to wait. Okay. Sorry, you have to do a transmission of the ACK. This is receiver getting a data packet and then sending out its ACK packet. So it has to send out the ACK after a certain amount of delay. This is that delay. The ACK delay is right here. Okay. So how is this going to play out in terms of implementation? I'll skip this because this is of not much importance to you. I'll go and show you our experimental setup. The experimental setup comprises of an RX and a TX. This is a Nordic development board. This is the ADF. This is an ADF board. And this is the 840 board. We had, as I said, made a commercial buy of the radio. And we have this Nordic development board. One is a TX, one is an RX, identical systems. Will they communicate is the question. Will we be able to code as per the standard is the question. And then we'll see what actually happens. All right. So now you see, just to elaborate on the state machine, you have the idle state. They're all powered down essentially. So you have to give a kick as you're doing power saving mode so that they come up, they get enabled, configuration registers, as well as the packet RAM is accessible. All of that you should do in this state. So this state is shown like a circle, but there are many operations that you have to do before you can start going from idle state to some other state. Okay, so that is written here in a very crispy manner. Similarly, once you come to fire ready state, the frequency synthesizer is important. You have to ensure that it is enabled and the system calibration is carried out. And then you receive and transmit blocks. The receive and transmit blocks are not enabled in this state. So you still don't do anything. Don't touch these blocks when you are here. Okay. Then in the TX state, you do that provided your RF frequency synthesizer is automatically calibrated, or you wait until the calibration is completed and you get a message that it's calibrated, and you have following a programmable delay period, the power amplifier is ramped up and transmission is initiated. Okay, so that is what you do. Then in the reception state, the RF frequency synthesizer is automatically calibrated, because if you are doing a transmission and waiting for an acknowledgement, you don't have to repeat the procedure. So it's automatically calibrated. And you can wait for a ACK packet to come back. Now, before transmission, you may also want to do a CCA check. And that's what is another state here. You, by default, upon completion of the clear channel assessment, the ADF automatically reverts to the state from which the RC CCA command was issued. So you can see that it was issued from fire ready state. So it goes back to fire ready state. Then you can push directly to TX, RC underscore TX you can issue, and then you can push the data packet to the radio controller's memory. That is possible. So there are these three cases which you see here. Case 1 is idle to 5 ready to RX. Case 2 is idle to 5 to TX, and case 3 is 5 to RX, TX, 5 to idle. Okay, all these 4 states. You can clearly see that it is going from idle to 5 ready to reception state. So this is actually coded, and we are watching this on the J-Link viewer, and it's able to print out that. Similarly, you see that it is doing the same here. It is in idle, goes to fire ready, and it goes to transmission state. And yeah, same thing here, all done here. So essentially, our the FSM transitions are tested on this ARM and ADF 7242 setup. And the implementation of the timer API and interrupt management is a very critical thing. So we have to implement that so that the state machine and its associated timing related parameters are met. And maybe Sahana, you can explain from here, and perhaps also the next slide, and we'll see. Yeah, go ahead.
So in each state, how much time has to be spent in the each state of the FSM is decided by this timer. All the time units are in microseconds, because here we have got 16 megahertz frequency. When prescaler we set it as 4, then we'll get the 1 megahertz frequency, that is nothing but microseconds. So all the state machines will be in the particular state
for a duration in the microseconds unit of time. So this is how interrupts and timer has been implemented for TX time slot and RX time slot. This is nothing but full TX time slot and this is nothing but full RX time slot. Timing parameters have been written here at the top of the diagram. So these blue arrows are all the commands and red arrows are all the interrupts that are required for the TX to enter into the TX state and to transmit the data packets at the TX state. So these colors depicts the different states of the mission, state mission. So this is idle, fire ready, RX state, TX state, CCA, and these arrows represent the interrupt data, acknowledgement, and the command. So first in the TX time slot, as we all know that TX state can be entered from idle state by issuing the RC fire ready command from from idle state, it will enter into the fire ready state. And in the fire ready state, it will enter into the CCA state by issuing the RC CCA command, that is 3. So in CCA state, it will perform the CCA operation, clear channel assessment, whether it will check whether the channel is idle or busy. So CCA is required only if the channel is shared link. So then after performing the CCA, it will revert back to the fire ready state, and then upon issuing the RCTX command, it will enter into the TX state. Yellow is nothing but the TX state. In TX state, it will transmit the data and then it will enter into the RX state upon issuing of the command RCRX, and then in the RX state, it will wait for the acknowledgement. And this is how the transmitter time slot works. Same goes with the RX time slot. It will first start with the idle state. Upon issuing of the RC fire ready command, it will enter into the fire ready state, and from fire ready state, it will enter into the RX state upon issuing of the RC RX command, and then in the RX state, it will receive the data transmitted from the transmitter, and upon reception of the data, it will enter into the TX state in order to transmit the acknowledgement to the transmitter saying that the data has been received successfully. So this is how RX timer slot goes, and these are the timing parameters that are associated with the RX time slot.
Great, thank you, Sahana. But if you look, folks, carefully on top, you have MAC TSCCA offset, MAC TSCCA, and so on. Now I'm sure you understand this is what we were trying to do here, right? We are trying to do exactly this. Okay, so this is what is defined in the standard down below. This is what was defined in the standard. You converted this picture, which you saw here, into this picture. Exactly as per standard, it has been implemented. And now, how good is it doing? That is the next question, right? So here you have to look at the implementation and its associated results. So let us go directly to the results part. But this is the section related to the transmission side. Okay, creation of the transmission time slot. Yeah, okay. And this is a creation of the transmitter time slot. We can skip this. We can also skip this creation of the transmitter time slot 4. We can skip this also, I think, because this is what is important. Sahana, go ahead. Explain this picture now. What are your results?
So as we saw in the previous diagram, TX time slot, we were associated with the timing parameters of CCA offset, CCA, RX, TX, max, TX, add delay, add wait. These are all the timing parameters associated with the timer slot. In the standard, they have specified the values for the 10 milliseconds time slot. In a time slot, these all things should be performed in the time transmitter side. That is, from idle, it will enter into the fire ready. From fire ready, it will enter into CCA and then perform CCA, and then again it will revert back to fire ready. Then from fire ready, it will enter into TX state and transmit the data, and then enter into fire ready again, and it will revert and it will enter into RX state in order to receive the acknowledgement. All these states are to be in the timely manner, and that is specified in the standard according to this. And these are the standard specified parameters for the 10 milliseconds time slot, and these are the experimental results that we got with respect to the transmitter time slot.
Okay, thank you. In some places, we have exceeded what may have been recommended by the standard, but that is okay, because as long as the receiver is able to negotiate and accept these parameters, a successful transmission is still possible. It's nothing that you should match the left side one. As long as your peer is able to receive it and you negotiated those numbers, that is already good enough. That's all that is important as far as the standard is concerned. By the way, we can also show you how the standard looks, and we can spend a little time there as well. Yeah, this is another one, right? This is creation of transmitter time slot. What is this? Is also the same thing. Right? Yeah, this is also another set of results. There was a slight exceeding in time here. This is for 10 milliseconds, and this is for 15 milliseconds. This is two different experiments for two different time slots that are mentioned. Okay, now this is time slots, timing parameters. Yeah, and this is interrupts. I think we discussed this already. This is the data frame format of the 15.4e TISH packet. As I said, this is people who know about the area quickly realize that this is a LLC type of frame format. Yeah, go ahead. What is your validation of transmit? What are your results here? Sahana, go ahead.
So can we go to the interrupt slide?
Yeah, sure.
Yes,
Yeah.
So in order to achieve the transmitter time slot section, first we will be validating the data transmission as shown in the next slide, data format. According to the data format, we'll be framing the data packet, and then we'll be transmitting the data continuously and receiving the data continuously. So that is shown in the next slide. So in this slide, we have kept the node continuously in the transmitter state, and we have kept another node continuously in the receiver state. So we are able to transmit and receive the data packet successfully with the numbers associated with each packet.
Thank you. So what we have not shown you, which is hard to show on a PPT, is in fact it can channel hop and do this transmission. What we are showing you is on a fixed channel essentially. We have taken one channel on which it has hopped and it is sitting there, and this is a snapshot of that particular frequency. Folks, I hope you are following. If you have questions, you should ask. Okay, this is a continuation of that, and I think this is a video. Maybe we can play this video. This is continuously transmitting. Yeah, we can try this. You're able to see the video? You're able to see the video?
Yes. Yes.
Okay. So you can see we put in hello world on the transmitter side, and then it was able to receive successfully. Okay, this is the state machine transition. It's not enough if it is doing transmission and reception. You also have to verify whether the state machine is implemented correctly. You can see from top: idle, phi, CCA, then TX, then back to RX, and acknowledgement there, and so on. So this is important. You should be able to get back. You should be able to trace the state machine as well. And this is another video which is talking about the state machine. It's a very simple state machine. Essentially, this is capturing a transmission. So you start with idle. What you want to do is you want to do a transmission, but before you do a transmission, you must go to phi ready. So it goes to phi ready. From here, it goes to phi ready with RC phi RDY. Then from there, it might go to CCA. Right, it does a CCA, RC CCA, comes back, and then goes to TX state. Then does a transmission, and then goes back to phi ready, and receives the packet. So all of that is captured in the state machine picture here, which is clearly indicating that it is transmitting and all that. Okay. So yeah, we can go on like this. Take it here. Okay, very good. Great. This is on the receiver side. Okay, the same thing. The receiver, what does it say? The standard says you should have MAC TSRX offset plus some time, which is MAC TSRX wait. Then you wait for RX on. You have to wait for the frame. There is some delay, some offset is there. That is this offset time. After that, you have to wait for MAC TSRX wait time. And from there, you wait for the packet reception. Then you give a MAC TX ACK delay. And then you transmit the ACK back. And that should be completed within this time. That is also important. Up to MAC TS max ACK, you should complete the TX of the ACK. So that is also something that we did. And I'll skip all this because these are not late. Same thing. And now these are some results. Sahana, you want to explain these results?
So in the receiver time slot, we saw that we have the offset times, wait time, ACK delay, MAC, maximum ACK. So these are all the specified values as per the standard for the receiver side. And these are the experimental values we received, we got at the receiver side for the 10 milliseconds time slot. In each time slot, these are all the timing parameters for the receiver.
Okay, very good. Yeah, so this is continuation of that. I think it's for a different time slot, 10 and 15. So this is fine. Yeah, this is some results here. Yeah, this is another video which essentially captures the same test bed. This is transmission and reception of beacon frames. So this is another thing, right? About, you recall in the first picture I mentioned to you about scheduling. In the scheduling part, beacons are also important, and this is a beacon scheduling part. You have anything to add, Sahana, or it's okay? It's okay, right? So this is just, it contains the size of the slot used in the network, the current ASN, information about the slot frames and time slots the beaconing node is listening to, 1 byte join priority if any, and all that. So this information, this EB is already good enough to ensure that the whole system gets synchronized, and because all time related information is carried here. These are some results of continuous transmission and reception of beacon frames. And this is another video, which I'm not sure whether it will be very useful for you. But then this is one part. There are other parts that you may want to try. This is on the one side, you can do all these things if you have, let us say, embedded controllers in your mind. But if you really want to reach out to long distance, you need really powerful transmitters, and therefore long range part of it may actually come from a different hardware platform. And so we switched all what we showed you there. In parallel, we started working on GNU radio. Okay, and so we have a GNU radio implementation of this complete system in our labs here, and Ipsita will explain a little bit about what we have been doing in this space. So she has made progress on channel hopping, clear channel assessment, develop a out of the tree module for TDMA and channel hopping, implementation of ACK frames, enhanced beacon generation and transmission, and so on. So all of this was done by Ipsita, and so let's see how she has done the channel hopping part. Over to you, Ipsita. Maybe you can give an overview.
So I'll start from CCA.
You'll start from CCA. Where is that? Next. Okay.
Next.
Yeah. Okay.
So as we saw in the previous slides, the CCA basically consists of 3 timing fields. First, there's the offset, and then there's the actual CCA performed in the MAC TSCCA, which is actually, as per standard, should be completed in 128 microseconds. So for implementing CCA, we sampled the received signals. We performed an FFT, and then we took the magnitude square to get the power. And then based on the power, we had a decision-making module, which made decision whether the channel is idle or it is busy. So we have a concept of hierarchical block in GNU radio where we actually implemented the previous 4 steps discussed. And this hierarchical block, which is shown here, is then built, and it is attached to the main GNU radio flow graph. So the CCA hierarchical block is as highlighted over here. And then first, so since USRP source is the place where we get the signals, so first it passes to the CCA block. We measure the channel parameters, and then we go to the actual MAC performing the MAC functions, and then the file box. So in order to estimate or validate whether the CCA block was working fine, we did some few experiments. So the first experiment was to know whether the CCA block will be able to measure the energy correctly or not. So we have 2 USRPs. The TX is USRP N210 and the RX is USRP P210. And then we use a Lime SDR for creating noise. So these are some of the results what we got. So as we increased the transmitted antenna gain of the noise source, we saw that there is significant amount of packet loss, and also the energy increased significantly of the channel, which is mainly contributed due to the increase in the TX gain of the noise source. So hence we concluded that our CCA module was working perfectly fine. So this is again another setup where the noise source is mobile and it's moving away from the transmitter and close to the receiver and vice versa. And these are the results, some of the results related to that. So this is just a graphical representation of the noise estimation of the channel. So the y-axis basically represents the amplitude versus the time. So as soon as there is high noise in the channel, so we got around minus 41 dBm as the noise in the channel, the maximum noise in the channel, by using 2 set of noise creating source, that is the Lime SDRs. So the main parameter in CCA is the noise floor level. So in order to determine that, we again had another experimental setup where we had a transmission mode and a noise creating mode and again a receiver mode. And we measured 2 ED threshold. One was in high noise areas, or a channel which is prone to high noise, and the channel which has relatively less noise. So, and we came to a conclusion that minus 18.68 dB should be set as the noise threshold when when we are working in a high noise area, and minus 58 dB is okay when the noise is comparatively less. So these are the graphical representation of the highest noise recorded and the lowest noise recorded in the channel. Then we have a small video on this video basically shows the CC assessment and the graphical representation of the TX side, RX side. So this is the CCA higher block, and then we have the GUIs, which shows the noise, and also the noise is shown numerically here. And then we also have the constellation diagram shown below. So then coming to the out of tree module. So out of tree module is basically any module which is developed out of the actual GNU radio source code. So it is basically developed for customizable functions, or if any functions is required by the user which is not available inside the GNU radio tree source, we can develop an OT module from scratch. So basically here we have developed 2 of them. The first one is to actually form the frame structure, the slot frame structure of 15.4e. So if we just attach this out of tree module properly to any GNU radio flow graph, we can actually implement the 15.4e functionalities. These are some of the results to validate that the out of tree module is working properly within a 10 millisecond time slot, and also we have frequency hopped for 4 frequency channels, not more than that. So this is basically a video of the working of the out of tree module. Then we also went on to implement the ACK frame in another out of tree module. The ACK frame, the data frame, and the enhanced beacon, all of them are generated and transmitted by the help of another out of tree module, which is called as the mac.cc. So this is the typical ACK frame structure, which is there in the standards. And we have implemented this in an array data structure. And here we can see this is a Wireshark log where we have the data received at the 20-second time slot. And we can see that immediately after the data is received, we have an acknowledgement packet generated and transmitted from the receiver. And then the same acknowledgement is received at the transmitter end also. So coming to the enhanced beacon, I hope Sir and Sahana has explained much details about why this enhanced beacon is needed in TISH 4E. So this is a typical frame format again of the EB, which is implemented in form of an array structure in GNU radio as well as in the ADF side. And we have transmitted the enhanced beacon at every 0th time slot of every slot frame. So this is the log in the terminal on that. So we can see that with the transmission of enhanced beacon at 1.22 gigahertz, we are also able to transmit other data packets at different frequencies. So this clearly shows the channel hopping and also the transmission of the enhanced beacon at the 0th time slot of the slot. Yeah, and this is the Wireshark log of the EB received at the new node at periodic time intervals. So this is it from the GNU radius.
Yeah, you can mention the future work. We have a lot of work going forward. Quite a few things to be done. As I said, we have to do compensation for temperature and the drift that is associated with it. We have to learn the drift. It's not learned, learn the drift rather. Sorry. Drift. Okay, and back to full screen. You can see my screen, right? We have to do that. Then we have to create the soft MAC from the commands. Essentially, applications will start with association, disassociation, and beacon request and all that. So we need to do mapping of all those requests which come from upper layers. We also have to do creation of the MAC services like slot frame request. I want to confirm link request and link confirms, everything related to the communication part. Then implementation of CSMA, CA slots for shared links. We have done the implementation quite okay, but then we have to do a lot of testing. Basic code is there. We need to do, quite detailed testing of that. And implementation of CSMA, CA retransmission algorithm. This is essentially required when we said that if you have a dedicated link and you want to ensure that data the channel is good enough for transmission, but then you want to get an acknowledgement that it has actually reached the destination. Otherwise, you may want to do a retransmission. Now, how to set the retransmission is indeed a challenge. Okay? So all of that will have to be tested, and that's a very critical part. So with this, there is the presentation is done, but there is still something which we can show, and that is the actual standard. Okay, so I'll just stop now and discard this, and I will still show you. Stop sharing this for a moment. Yeah, stop share. Give me a minute and I'll put back the standard. Okay, I'm back. So let me just flash the standard for you. This is this file. So do you see the standard? Do you see the screen?
Yes.
Okay, great. So this is the 15.4 2020 standard. As you can see, folks, this is really quite a hot area, and implementing this standard is also equally exciting. And let me take you directly to Control F, which is the page. Here we go. 380. Here. Which one? 387. Yeah. Okay, there you are. This is the TSCH MAC PIB. Yeah. Where is it? This one. Huh? So you see, folks, what we showed you is a snapshot of this table. This one, this particular table, which is 899. Is this the one?
Yes.
899. You have MAC time slot template ID. It tells you that this is what I was mentioning about the negotiation. I'll give you an idea of that. If you go to MAC time slot template ID, this is what it's transmitted by the node. It's an integer type. There is a range for it. An identifier of the time slot template. You can push that value, whatever you want to define, by filling up that range, essentially by picking a number from there. That will tell you the template. That will give you the template information. And the number has some, there are already, the standard already gives you some defaults. The default is there. You can see for 2450, the 2.4 gigahertz, it is 0x00. Now you see MAC TSCH offset. It says it is 1800 microseconds. Okay, the time between the beginning of the time slot and start of CCA operation in microseconds. MAC TSCCA, duration of CCA in microseconds, 128 microseconds. MAC TSCH offset. What is this? The time between the beginning of the time slot and the start of the frame transmission in microseconds, 2120. So you have to get to nuts and bolts of each one of these MAC attributes, they're called PIB attributes, and then you have to write small code, small pieces of code, use your timer implementations, which we showed you, and ensure that these timing requirements are actually met. So that is the challenge in developing the MAC. So you can go and look up other attributes also. Your MAC time slot template ID, it's a continuation of all the terms that we refer to are out here. MAC TSRX offset. What does it mean? Beginning of the time slot to whenever the receiver shall be listening in microseconds. MAC TSRX ACK delay. Again, one more cryptic term. End of frame to when the transmitter shall listen for acknowledgement in microseconds, and so on. You can go on reading like this, understanding how exactly the whole system will have to be implemented. Look at pictures, look at papers which are appearing, and then essentially code all of that into the into C code, also into the out of tree module which Ipsita mentioned, and get to an implementation. Obviously, this project is only 1 year old, actually a little over a year old, and we could go only that much distance. Hopefully, if we have a meeting similar a year from now, we should have sufficient amount of implementation of this TISCH system. That's essentially what I wanted to share with you, the development of what we did in the lab and the ongoing work that is happening in the lab at the moment. If you have questions, I'll take. Otherwise, I'm done with whatever we wanted to show you in this tutorial. Preetham, over to you. Hello, Preetham. Hello, Preetham.
Yeah, give me 1 minute. Can you hear me?
Sure. Yeah, very well.
Okay. Yeah. So thank you, Dr. Prabhakar, for the excellent talk and working not just with the standard and nuances, but also showing the working through a live board, which very rarely you get to see in the sessions and classes. So I think this participants must have gotten a very good the inside view of how these things, boards and systems are designed and programmed in real life.
Correct. So Preetham, what I did deliberately is I did not show the standard to begin with, because that can be very overwhelming. You have to read those 800 pages.
True.
Instead, what you do is you start an implementation, take a small problem, start the implementation, and then work backwards.
Right. Definitely the standard can become daunting at the beginning for a novice. So
yes.
This it was really effective that you started with some whiteboard kind of explanation and then work through the examples. So that worked out to be quite intuitive approach, at least to me. I hope the participants could follow it through. And do we have time for any questions?
I am here. I love to take questions because
Right.
it will be the best way to learn, actually. Go ahead, ask any question.
Yeah. So participants, do we have any questions on specifics of this chipset or the standard or the IoT standards in general?
Sir, I have a question from the beginning of the session when Hello World was being transmitted and received. So there was some instance when there was some garbage value actually being received. So was that happening due to some like receiver offset, something?
You asked a beautiful question. I will give you the answer to this. Okay. Okay, that's a wonderful question. Wait a minute. So I should stop sharing this. I'll tell you where the problem is. So let me stop sharing. So great. Then let me go back to my presentation, which is, give me a minute. Huh?
Yes.
The slide deck, which is, it's okay, we can take this. We can also take this one. Yeah, this one we can take. I'll show you one picture and you'll actually know the answer to that problem. So let me go back to share. Yeah, see, down this one. You see my screen?
Yes, we can see.
Now you know the answer. I mentioned to you clearly that we have not done this at all. What we have done is this. This is done. To some extent, this is done. So I'll put a smaller tick here. This is not done. And I believe strongly that we should not invent anything new. That's why we are holding on to this. And our current investigation is to see it's very rich in literature, I mentioned already. Very rich in literature. Why should we invent one more? I'm sure there's already something very, very suitable for 15.4 ETISH. So that's the point. You take that algorithm, try it out on as a OOT module on the GNU radio, and then see if it synchronizes well. First of all, you should get the implementation of the synchronization algorithm correctly. So you need high-level tools. So that's why we do the GNU radio. Once you know that the algorithm is coded properly, you get a hang of it, then take it into embedded programming and then implement the time synchronization of it. So this is holding off. So the garbage you see is only because of that.
Okay, sir. Thank you, sir.
So Jatin has posted a question on chat. Jatin, would you like to unmute yourself and ask?
Yes, sir. Good evening, sir. Sir, right now I'm very much interested to learn about system on chip designing, sir. And unfortunately, I was not able to find any kind of resources or courses that I can take up and learn about SoC, sir. So, are there any resources for me to learn about system on chip?
Sure, I can see the whole idea of system on chip is several components of the hardware get integrated into one single silicon. You have radio coming into silicon. You have power supply coming into silicon. You have flash memory coming into silicon. RAM is into the same silicon. CPU is out there. All of this, right? Including nowadays the balun of the RF transmitter is also into silicon. So if you want to study SoC, you have to study each one of these components independently and then look at the SoC in a holistic manner. I'll give you an example. You take companies like TI or you take any big company, none of them are experts in all the components of the controller that they release, the SoC that they release. For example, ADC may be coming from some other company. They may take the IP and then integrate it into their SoC. So the IP which they get has certain performance and maybe one LSB plus minus one LSB error in ADC, some gain error, some error, offset error, some differential nonlinearity, integral nonlinearity, and so on. So those errors are all characterized by that vendor, and that vendor will give the IP. And essentially, he'll give some VHDL code or something, which TI will take and nicely integrate it into their system. Therefore, understanding individual blocks is not a bad idea. Now you take TISH. TISH, you don't have to worry. Actually, if you go and take Nordic 840 board, it supports both the radios. It supports Bluetooth low energy. In one click, you can change it to 15.4e TISH. Now you can't go and read up everything there. So understand the standard very well and see how much of the standard is actually implemented by the Nordic folks. That's the way to go about if you want to understand the SoC.
Okay, sir. Okay, sir. Thank you, sir.
So I had a question which is not directly related with 8.15.4 or E or TISH. There are these inexpensive RTL SDR radios. I think they use they implement GNU radio, but they work out very cheap. So is it possible if someone wants to work on a different newer MAC protocol or just to try out a MAC protocol, it's possible to come up, design a new MAC and implement it on those RTL SDR kits?
Wonderful idea. You should try. For 7,000 rupees, you will get 5 to 7,000 rupees. You will get SDRs. Wonderful idea. You should buy enough of them. Ask your college or wherever you are working to buy them. If not, buy them yourself because they are not very expensive. Wonderful idea. You can try. Number one. Number two, forget about coming up with new protocols. Even to understand the protocol, you need to practice. For example, Wi-Fi 802.11b is out there already. GNU radio blocks are available. What stops us from going to GNU radio, pulling out the blocks which are there, trying to see step by step how is it that they integrate one block to the other? How is transmission coming about? Does it work with a commercial, let us say, Linksys or D-Link Wi-Fi system? What is that beauty? How does it work? What data rates you get? All that you can actually do. Wonderful amount of work you can do. Your idea is very good. Excellent. Please go ahead. Hello?
Are there any other questions? If not, then maybe we can thank Dr. Prabhakar for an excellent session on IoT and the demo. So just thank him, and hopefully this will inspire the participants to try out experiments and take up some research projects in this area, and also explore the available chipsets and SoCs to develop some proof of concept solutions using these chipsets. So thanks once again, and thanks for joining.
Sure. Thank you. Thank you very much, Preetham. Can I leave now, Preetham?
Yeah, sure. So we'll end the session unless participants have some feedback to share about the summer school format itself, or any feedback about all the sessions. Okay, so thank you so much for the 3 days of summer school participation in this summer school. So we will share the recordings on our CNI YouTube channel. So we have a YouTube channel, please subscribe to it so that we keep posting talk videos. We have a weekly seminar series also that we conduct on every Tuesdays, and you can join the seminars mailing list so that you can get announcement on the weekly seminars. And most of the talks are recorded and streamed for later viewing on the YouTube channel. So, and as we said in the beginning of the summer school, we keep announcing internships and project openings at CNI on our webpage. So those announcements are put on our social media accounts as well as the website. So I would request you to keep visiting our website for the recent updates. So thank you so much, and hope to see you, some of you, for subsequent events at the CNI. Have a good weekend.
How do we see the seminar, sir? Are there on the website? Or?
Yeah, you can go to our center website and you will see the announcements on the weekly seminars.
Okay.
So there is, I'll post a link to the seminar series also. I'll just put it on chat. Okay, I've shared the link on the chat, so you can visit that for. And other events we announce it on our website. Okay, so thank you again, and have a nice weekend. We'll end the session as well as this concludes the summer school CNI 2021 summer school.